Hey Chem students, this is your first lesson in the Reaction Rates and Equilibrium unit, and today what we're going to be focusing on is reaction rates. So three basic goals for this lesson. First of all, identify different factors that we can change in order to either speed up or slow down a reaction. Second goal is to be able to calculate the rate of a reaction using appropriate units for that. And then third, talk about a catalyst, which you may have talked about previously in biology, but we'll dive into it a little bit more from more of a chemical perspective and what that really does in order to speed up a reaction. Right. Now, in order to consider all these things, we first have to think about what really is occurring in order to have chemicals react with each other. So we know that we can start with a couple of chemicals, different molecules, and somehow they go from being one set of molecules, one set of substances with certain bonds, and suddenly we end up with new bonds and new substances as a result of that. The question is then, what exactly happened? How did we go from our reactants to our products? And our current understanding is that the key idea behind reactions is molecular collisions. So that in order to have reactions where we are changing the substances, breaking bonds, forming new ones, we have to have molecules hitting each other hard, right? So we can see sort of a little diagram of that, of a couple different collisions. Now what you may notice is that collisions are very common because obviously we've got lots and lots of molecules. There's no shortage of those in the universe. We've got lots of them. And they're moving pretty darn fast. So molecules are very frequently colliding with each other, but depending on the conditions, they may or may not form new bonds and create new substances. So we see with this upper collision, the way that the two molecules hit each other worked out really nicely so that we could get a reaction and form two new substances. Whereas in this lower reaction, we see that just the way the two molecules hit each other, it didn't really favor an actual chemical reaction and a change of substance as a result of it. So we get lots and lots of molecular collisions, and sometimes we end up getting reactions as a result of that. But a precursor to any reaction happening, in order for us to ever break up bonds and get new ones to form, we've got to have our molecules colliding with each other. That's our current understanding. We've got to have those molecular collisions in order to actually have any sort of chemical reactions occurring. So if we want to get a reaction to happen faster, if we want to increase the rate at which reactants are breaking bonds and forming products, basically, all we have to do is increase the rate of collisions. The more collisions we get, statistically speaking, the more likely it is that we'll get reactions occurring. So the factors affecting reaction rate, that first goal of ours, are just the ones that are going to increase the rate of collision. Now we've got 5 of them for you to consider. The first one being temperature, and this is probably one of the easier ones to understand. So if we increase the temperature of a substance, what we're doing is increasing the kinetic energy of its particles. We're getting those molecules to move faster. All right? And if they move faster, they're more likely to collide with each other because they're both moving faster, and so they're going to run into each other. And that increases the rate of reaction as a result of it because we're getting more collisions happening. You can see this in particular, obviously, like in cooking, for example. The reason we raise our substances to high temperatures is to increase the reaction rate so that we can get those chemical reactions to occur more quickly in our food. Another place where we can see this is with glow sticks. So if you've ever had a glow stick, what you might have heard people tell you is to store that glow stick once you've broken it and activated the reaction between the different chemicals in that glow stick. They tell you to put it in the freezer and it'll glow longer. And the reason for that is when you put it in the freezer, you're lowering the temperature, so you're decreasing the rate at which those two chemicals are colliding with each other, which means that there's a slower rate of reaction. They're not going to give off light as brightly or as quickly. If, on the other hand, you wanted to have like a big, bright display from your glow stick and get it to shine as brightly as possible, then you'd want to bring it out somewhere warm where you get a faster reaction rate and more light being emitted as a byproduct of that reaction. So just a little something for you to consider. Second factor affecting reaction rate is concentration. Okay, so this one, again, is, I hope, pretty intuitive. If we increase the concentration of a particular substance, that simply means we've got more of that substance. And the more of those particles we have, the more collisions we're going to have as a result of that as well, which again means a faster reaction. Now, another thing that we can do, which is in effect kind of the same thing as increasing concentration, is to increase pressure or decrease volume. Now, when we either increase the pressure or decrease the volume, what we're doing is we're forcing those molecules closer together. And when we're pushing them all into a cramped space, they're gonna bump into each other more frequently. And that means a faster reaction, more collisions between those molecules. A fourth factor for us to consider is the actual structural characteristics of those particles that we're dealing with. Some of them, just based on their size, based on their geometry, they're going to have more stuff sticking out. It's going to be easier to break them apart. Whereas other compounds might be a little bit more compact, a little bit more geometrically solid and stable, which would make it harder for them to break up and decrease the reaction rate as a result. Okay. And then the fifth factor for us to consider is the presence of a catalyst, and that's what we're going to be talking about next. Is basically what a catalyst does to actually increase the rate of reaction. Okay. Now, to just dive in a little bit more into what exactly is going on when our molecules collide. When our molecules get closer and closer together, those interactions between the two of them, between their the electrons of one molecule and the electrons of another molecule, cause the orbitals to distort. Now, again, the orbitals are those different energy levels where the electrons are basically staying and orbiting within. So as our two molecules come closer together, their various electrons repel each other, and that kind of throws off the shape of our orbitals. And as we throw off the shape of those orbitals, it weakens the bonds between the different atoms making up those molecules. Because again, bonds are all just about sharing electrons. So if we're kind of throwing off those electrons and kind of pushing them out of their usual pattern, it's going to be easier to break apart those bonds and get those atoms to separate. And once the atoms separate, then we have opportunities for them to meet up with new atoms and form new substances. So that's really why it is, what's going on down at that like subatomic level when we get a collision and a reaction occurring. Now, basically what a catalyst does is it makes it a little bit easier for the bonds of our reactants to break apart, and then that's going to make it a little bit easier for the bonds of our products to form in the absence of those pre-existing reactant bonds. All right. So to dive into the work of a catalyst a little deeper, we're going to look at a diagram. Okay. And this is not something that you need to be able to create, but it is something that you should understand. So what we see here is an energy diagram describing the amount of energy stored up in our substances. Okay, so along the y-coordinate here, we've got the energy of our substances, and along the x-coordinate, we can kind of think of it in terms of time, as time goes forward, what we've got. So on the left-hand side, we've got the energy of our reactants, the substances that we're starting with, and over on the right, we have the energy of our products. Okay. So in order to see what's really going on here, let's narrate the story of two molecules getting ready to collide with each other. Okay, there are two molecules. Aw, they're cute. Okay, so what we find is as the molecules get closer and closer together, again, those interactions between their electrons will cause the bonds to weaken as the orbitals get distorted, and that causes an increase in the stored energy within our reactants. Okay, so as they get closer together, those orbitals distort, the electrons are kind of thrown off. It's a higher energy state. There's more energy stored up in our reactants at that time. Okay. Now we reach the absolute maximum amount of energy at the moment that those molecules essentially collide. It's the closest they get together. It's the most distorted the orbitals get. That's the moment when bonds are broken because they can't handle that additional energy anymore. Right? And then what we find is new bonds are formed as a result, and as our newly formed products then move apart, they've done their thing, they've collided, they've formed their new bonds, and now they're ready to move on. Okay, as they move apart, we see a decrease in energy because they're not kind of fighting with each other anymore. We don't have those electrons repelling each other. So as they move farther and farther apart, there's less and less energy. Okay, so that's basically the story of what's going on energy-wise when we have a reaction. Our reactants start with a certain amount of energy involved. As they get closer and closer together, that's a higher and higher energy state that they've got as their orbitals are distorting. And then once they form their new bonds, the energy drops back down again. Whew. Okay. So we can define a couple of key parameters and characteristics of a given reaction. Okay. First of all, what you notice is that the reactants gained a certain amount of energy between when they were just hanging out by themselves to the time that they collided. Because again, as they got closer and closer together, the orbitals got more and more distorted. They were in higher and higher energy states. Now that amount of energy that we saw increased between our starting point and the time of collision is called the activation energy. That's the minimum amount of energy that the reactants need to gain in order to finally collide and form new products. Okay, so we call that the activation energy, just the change in energy from start to the time of collision. Now the rate of reaction is going to depend on the amount of activation energy. The more energy it's going to take in order to get a reaction, the slower the reaction is going to happen. Okay? Just like you trying to climb up a hill, you have to put a lot of energy into that. The taller the hill is, the longer it's going to take you to get up there. Okay? Same for molecules. The greater the energy increases, the greater the activation energy, the longer it's going to take for us to have a reaction actually occur. All right. Now what a catalyst does is it's a substance that speeds up the reaction without actually reacting with our reactants. It basically just kind of serves as a go-between or a matchmaker, you could think of it. It's just something that sort of facilitates our two reactants colliding with each other without actually getting involved in that mess itself. Okay? To go back to our hill analogy, you could almost think of a catalyst as being something that like bulldozes a new path through the middle of the mountain for our reactants to get through. Okay, so basically it decreases the amount of activation energy required to get our two molecules, our two substances, to collide with each other. Okay, and that lower activation energy, the less energy it takes, the faster our reaction can proceed. Okay, so let's just look at an actual example of this. Okay. So here, for example, we've got a platinum surface. This is one example of a catalyst that could be used. In biology, you probably heard about enzymes that serve as catalysts as well. So we can kind of see on the atomic level what a catalyst is really doing. Okay. So right now, this plate of platinum is serving as our catalyst. Okay. Now what we see is that it attracts hydrogens. So our little hydrogen molecules are like wandering around through the air, and as they interact with the platinum, they go, oh, we want to bond with you. So the hydrogens break their bonds with each other and instead bond with the platinum. And platinum's like, cool, whatever, come hang out, life is great. Right? Now along comes C2H4. Okay. It comes along and says, oh, I would also like to be friends with the platinum. Right? So what we find is that the double bond between those two carbons, for example, would break and also bond with the platinum. Right? And then what happens, the platinum is sort of the central hub by which our different substances can meet each other. Okay? So our carbons hanging out right here can meet up with the other hydrogens that are hanging out on that platinum surface, and then they can hook up and leave again, now having formed C2H6. So what we notice is that the platinum wasn't then part of the new product. All it did was serve as kind of a meeting place for our different reactants to come together and form a new product. Okay, so again, kind of like a matchmaker. It's sort of creating these favorable conditions for our different reactants to actually meet up with each other. Okay, So that's the basic idea behind a catalyst. So that's our fifth thing that can increase reaction rate. Now, our last thing to talk about is how to actually calculate a reaction rate with numbers. Okay. Now, there are two ways to think about a reaction rate. One way to think about it is the rate at which we're losing reactant. Okay, because obviously the faster the reaction is going, the more of our reactant is turning into product. So if we see the decrease in the amount of reactant we have, we can kind of get a sense of how quickly those reactants are forming products. So that's one way that we could measure reaction rate. The other way we could do it is by looking at the rate at which new products are appearing. Also an option. Usually what we end up doing is looking at the rate of disappearance of reactant rather than looking at the rate at which product is appearing, but you could do either. All right. Now, if we wanted to graph the concentration of both our reactants and products over time, what we would find is it would look kind of like this graph that we have over here on the right. So as time proceeds, we start out with a certain amount of reactant, and then obviously it decreases over time as more of those reactants are turning into products. Same deal for the products. It starts out at 0, but then over time we get more and more reactants as a result, or more and more products, excuse me. More and more products. Okay. Now we define a certain time as equilibrium when we see those two levels kind of evening out. When we see that our amount of products isn't really changing and our amount of reactants isn't really changing. And we're going to talk more about that later in this unit. But just to get you started to think about it, the time at which the reaction rate isn't really changing anymore, when we've got a pretty stable amount of products and reactants, that's what we call equilibrium. Okay. Now, when we're calculating the rate of reaction, the units that we're going to use are some units for concentration over some units for time. So, for example, it could be molarity per second, it could be grams per liter per minute, it could be parts per million per hour. It doesn't really matter. Any unit of concentration over any unit of time, depending on what your data tell you. Okay. So basically, we can calculate this then based on the concentration and based on the time at which each concentration was found. So let's consider some data. Okay. Say we've got some hydrogen peroxide that we've got. And over time, we know that hydrogen peroxide is going to break down into water and oxygen. And we want to figure out the rate at which this is happening. So on the left-hand column here in our data table, we've got the concentration of hydrogen peroxide in molarity. And the right-hand side, we see the time at which each of these data points was taken in minutes. So if we want to figure out the reaction rate for the first minute that we were collecting data, what we would do is we would calculate the change in concentration divided by the amount of time that had elapsed. So for the first minute, between 0 and 1 minutes, we saw a change from 0.3 molarity to 0.221 molarity. So to figure out how much it changed, we just subtract those two. And then we divide by the amount of time it took for that change to occur, which in this case, from 0 to 1, was just 1 minute. We divide that and we determine that for the first minute of this reaction, we had a reaction rate of 0.079 molarity per minute. That was the change in concentration per minute during that time. Okay. Next, we might consider what was the rate between 1 minute and 5 minutes. Okay. And again, what we would do is we would just look at the change in concentration between 1 and 5 minutes, so 0.221 minus 0.107, and then divide that by the amount of time that had elapsed. Now, between 1 minute and 5 minutes, a total of 4 minutes have elapsed. So we would divide that through and get a total of 0.0285 molarity per minute. Okay. Same idea, between 15 and 20 minutes, just subtract the two values, the value at 20 minutes minus the value at 15, or excuse me, the other way around, the value at 15 minus the value at 20, divided by the 5 minutes that elapsed between those two data points, and we get 0.0020 molarity per minute. One thing you might notice that the reaction rate is changing, and in particular, over time, it's decreasing. Okay, we can see that also in our graph here, what you notice is that we start off with a very steep line, okay, which indicates a very large reaction rate. That slope is what tells us about the reaction rate. Okay, so we see big changes in little bits of time here. So that steep line indicates a very high reaction rate, and over time it kind of levels off, which indicates a decreasing reaction rate over time. All right, folks, that's all I have for you for now. Stay tuned for more information on equilibrium later.